Now we will talk about the example 1, a falling object. Suppose that an object is falling in the atmosphere near sea level. Formulate a differential equation that describes the motion. Solution. We begin by introducing letters to represent various quantities that may be of interest in this problem. The motion takes place during a certain time interval, so let us use t to denote time. Also, let us use v to represent the velocity of the falling object. The velocity will presumably change with time, so we think of v as a function of t. In other words, t is the independent variable and v is the dependent variable. The choice of units of measurement is somewhat arbitrary, and there is nothing in the statement of the problem to suggest appropriate units, so we are free to make any choice that seems reasonable. To be specific, let us measure time t in seconds and velocity v in meters per second. Further, we will assume that v is positive in the downward direction, that is, when the object is falling. The physical law that governs the motion of object is Newton's second law, which states that the mass of the object times its acceleration is equal to the net force on the object. In mathematical terms, this law is expressed by the equation. Let us write this equation down. F equal to m times a. This is formula 1. Where m is the mass of the object, a is its acceleration, and F is the net force exerted on the object. Maybe we can try draw some picture. Use the red color. This is the object, and it's falling down to the ground. And here it has the force F. To keep our units consistent, we will measure m in kilograms, a in meters per second square, and f in newtons. Of course, a is related to v by a is equal to dv dt. So we can rewrite equation 1 in the form. Let's write it. The second formula or equation, F equal to m dv over dt. This is the second formula. Because a is equal to dv over dt, this is the derivative of v in terms of t. Next, consider the forces that act on the object as a force. Gravity exerts a force equal to the weight of the object, or m times g, where g is the acceleration due to gravity. In the units we have chosen, g has been determined experimentally to be approximately equal to 9.8 meter per second square near the Earth's surface. There is also a force due to air resistance or drag that is more difficult to model. This is not the place for an extended discussion of the drag force. Suffice it to say that it is often assumed that the drag is proportional to the velocity, and we will make that assumption here. Thus, the drag force has the magnitude gamma v, where gamma is a constant called the drag coefficient. The numerical value of the drag coefficient varies widely from one object to another. Smooth, streamlined objects have much smaller drag coefficients than rough-blunt ones. The physical units for gamma are mass over time or kilograms per second. For this problem, if these units seem peculiar, remember that gamma v must have the units of force, namely kilogram times meters per second square. In writing an expression for the net force F, we need to remember that gravity always acts in the downward positive direction, whereas for falling object, drag acts in the upward negative direction. Let's draw this. Maybe here is another force. Uh, this is the negative upward drag. As shown in figure 1.1.1. Okay, here is the official figure, m times g and gamma v. And we can write the third equation. So here F is equal to mg minus gamma. Oh, this is gamma. And V, this is the third equation. Because here we can change this F to mg, and in this drag, I think this drag is gamma v, and here is the total F. Where is the okay? And maybe the mg is longer than gamma v, the drag. And equation 2 then becomes, this equation 2 then becomes another equation. That is the fourth equation. Let's write down. Because this part is about the force, and this part is about the mass and the acceleration. So let's just put this thing, the right hand side part, into this position. We can get the fourth position. Let's write m times dv over dt. is equal to this mg minus gamma v. This is the fourth equation. Differential equation 4. Because here it is an equation with this derivative, so it is a differential equation. It is a mathematical model for the velocity v of an object falling in the atmosphere near sea level. Note that the model contains the three constants. The three constants is m, g, and gamma. There are three constants. The constants m and gamma depend very much on the particular object that is falling, and they are usually different for different objects. It is common to refer to them as parameters, since they may take on a range of values during the course of an experiment. On the other hand, g is a physical constant whose value is the same nearly for all objects. Next, to solve this equation 4, we need to find a function v is equal to v of t that satisfies the equation. This sentence means that what is to solve a differential equation? That is, we need to find a function, a specific function form v of t that it can satisfy this specific equation. It is not hard to do this, and we will show you how in the next section. For the present, however, let us see what we can learn about solutions without actually finding any of them. Our task is simplified slightly if we assign numerical values to m and gamma, but the procedure is the same regardless of which values we choose. So let us suppose that m is equal to 10 kilogram and gamma is equal to 2 kilogram per second. The equation 4 can be written as this, the fifth equation. Let's write down this fifth equation. dv. So how the fifth equation comes from? Because here now we just substitute the specific value into the m and gamma. So let's say m now is equal to 10 and then here, and gamma is equal to 2. So directly we can get 10 dv over dt is equal to 10 and g I think g is somewhere 9.8. So g is somewhere, where is 9.8? Let's find the g. Yeah, g has been determined experimentally to be approximately equal to 9.8. So here g is 9.8. So we can write 10 times 9.8 and then minus gamma is 2. and this is V. Okay, so here is the process. So in this situation, in this setting, finally, we can get this formula or equation. And now we just divide it. We just divide this equation on the left side and on the right side at the same time. Divided it by 10. What we can get is divided it by 10. Now it becomes dv over dt, and here we divide it by 10, so it remains 9.8, and 2 divided by 10 times v, and 2 divided and divide 2 by 10, it is 5. So here is 5, and here this is the fifth equation we get.